Hello class, I hope you are having a wonderful day. What I wanted to do in this video is work through problem number 2 on the assignment that is titled Apparent Weight and Acceleration. So this is problem number 2. I am going to read through the problem and I'm going to underline important information, and then I will show you step by step how to solve the problem. When a horizontal force of 8.95 newtons acts on a block on a resistance-free surface, it produces an acceleration of 2.5 meters per second squared. A second block with a mass of 4.2 kilograms is dropped on the first. Calculate the magnitude of acceleration of the combined mass if the same force continues to act. And we are going to assume that the second block lands perfectly on the first and it does not slide around. Okay? So let's say applied force. Let's generate a column of knowns and unknowns. So applied force is equal to 8.95 newtons. And it produces an acceleration of 2.5 meters per second squared. Okay, so the first thing we need to do now is use Newton's second law of motion to calculate the mass of our object. So we know that Newton's second law states that the acceleration of an object is directly proportional to the net force applied to the object and inversely proportional to the object's mass. So we need to calculate mass. What I'm going to do is multiply both sides by mass, and this is going to give me mass times acceleration equals the net force applied to the object. Now remember, we're looking for mass, so what I'm going to do is divide by acceleration on both sides of the equal sign. So this is going to give me mass, and I'm going to use a subscript here of B1. This is me just indicating this is the mass of block 1. This is net force divided by the acceleration. So net force is going to be our applied force, and that is our net force because we have a resistance-free surface. So we don't have any friction force working against us here. So net force 8.95. And let's go ahead and break down the unit of newtons. So we have a kilogram meter per second squared. And we're going to divide this by the acceleration that our net force produces. This is 2.5 meters per second squared. Okay, so let's go ahead and get out our calculator. 8.95 divided by 2.5. I get 3.58. Now let's take a look at our units. So in my numerator I have kilogram meters per second squared. In my denominator I have meters per second squared. So my meters and my second squared is going to cancel out, leaving me with units of kilograms. So we're going to need this guy right here. So what we can also do to kind of better understand what's going on, we can draw a simple picture here. So here is my surface. I'm going to say mass of block 1, 3.58 kilograms. Okay, and we have an applied force. Now I'll identify that by F sub A on my diagram. This is 8.95 newtons. Now, if we were to draw a free body diagram, it would look something like this. So here's our mass, so our system here. And remember that the arrowheads in a free body diagram always point away from the system. So our applied force is in the positive x direction. F sub A, 8.95 newtons. We have the weight force due to gravity, identified by F sub G. And to calculate the weight force, this is mass times the acceleration due to gravity. My mass is 3.58 kilograms. The acceleration due to gravity is negative 9.8 meters per second squared. This gives me a negative 35.084 newtons. Now remember, on your free body diagram, we do not need to provide the negative sign here because we have our vector arrow pointing in the negative y direction. So the weight force here on the free body diagram, we're just going to say 35.084 newtons. Well, our system is in equilibrium in the y direction, so that means the normal force applied by our surface is 35.084 newtons. This is an interaction pair, so forces are equal in magnitude but opposite in direction. Okay, and obviously we can see a net force in the positive x direction here. Okay, so it says calculate the magnitude of acceleration of the combined mass if the same force continues to act. So we're going to drop a 4.2 kilogram mass on top of the first. So in situation 2, here's my surface. Mass 1, 3.9, is it 5? Sorry, 3.58. Yeah, 3.58 kilograms. We're going to drop mass 2, which is 4.2 kilograms. And our total mass, so I'll use the subscript of T for total. I've got 4.2 plus 3.58. This gives me 7.78 kilograms. So once again, we're going to use Newton's second law of motion. So acceleration is equal to the net force divided by the mass. And in this situation, I'm just going to add that subscript of T for total mass because that's what we're taking into consideration in this situation. So the net force applied is going to be 8.95. And it's newtons, but once again, I want to break that down into a kilogram meter per second squared. And we're going to divide this by 7.78 kilograms. So it should be slightly over 1. 1.15. So acceleration is 1.15. Let's take a look at our units here. So remember, when we divide fractions, in my denominator, this can be kilogram over 1. We're going to multiply by the inverse of the denominator. So units, I have kilogram meters per second squared times 1 over kilograms. My units of kilograms will cancel, leaving me with units of meters per second squared. All right, so with an applied force of 8.95 newtons to the mass of 7.78 kilograms on a resistance-free surface, we experience a 1.15 meters per second squared acceleration. Okay, so this was number 2 on the apparent weight and acceleration assignment. If you have any additional questions or you need some help, please feel free to call me or send me an email. I hope you have a wonderful day.